recall that we have seen the definition of a tautology and contradiction. Yeah, and propositional formula S is said to be a tautology if it is true for all valuations. What is a valuation? Valuation is a function. It is a two-valued function from SL to truth or false, or equivalently from L. Yeah, I mean the function from SL to true false that satisfies certain conditions, whereas the function from L to true false does not need to satisfy any conditions. You understand that? Okay, a contradiction is a statement which is always false. Can you give me an example of a contradiction? P conjunction negation P is always false. P disjunction negation P is always true. And two formulas are said to be logically equivalent if their valuations are the same. Now, today what we are going to do in the first part is, instead of looking at a single formula at a time, we are going to look at a collection of formulas. Okay, so let T be a subset of SL. And now we want to define what does it mean for T to be tautologous. So say that T is tautologous if, can you guess what it should be? Yes, if V of S is equal to T for all, actually this is a bad choice, right? I should say S. I am going to make that change. We say that S is tautologous if V of S is true for all S in S and all valuations V. Okay, say that S is contradictory if, any guesses? If what? Loudly. Every element in S is contradiction. That's not the case.
For any value.
Yes. If for any valuation V, there is S in S such that V of S is false. So see, tautologous, there is no need to give me give any examples. Yeah, it's just a bunch of tautologies. Whereas here I need to give you some examples. So for example, P comma negation P is contradictory. You see that if a valuation makes P true, then this is false. And if a valuation makes P false, then this is false. So together, together it is contradictory. So basically what is happening that, I mean in very simple terms, if you consider the Lindenbaum-Tarski algebra, then these two elements or their logical equivalence classes, they will generate the full filter, the full Boolean algebra. Can you see why? If you consider P and you consider negation P, both of them are in the filter, but a filter is closed under finite meets. So therefore P is there, negation P is there, so their meet is there. What is meet? not 0, okay, or the contradiction. So basically this set together generates a contradiction. It is capable of generating a contradiction. Okay, that is what contradictory means. So it's basically like in real life also we'll do something like this, right? There is a group of friends and they have contradictory opinions. Correct? So one person says P, another person says negation P. So it's not that individually they are problematic, but as a group they are problematic. I mean their opinions are problematic. So they contradict each other. Yes? Okay. Now let us go back and say that S is say that S is satisfiable if there is a valuation such that V of S is equal to true for all S in S. You understand this? Satisfiable means some valuation. Yeah, there are so many valuations, but at least one valuation makes all the formulas in capital S true. Okay. Any problems? Can you give me one example of a satisfiable set? Singleton P, yes. Any other in two variables, let's say? Well, let's write something more complicated. For example, this is satisfiable. Yeah, given anything you can determine whether it is satisfiable, contradictory. What you had to do is you had to construct truth tables for all the formulas in capital S and make sure that there is at least one row of the truth table which makes all those formulas true. Okay. Any problems here? Let us proceed then. So these three are the basic definitions, and now what we are going to look at is how one statement is a logical consequence of a bunch of statements. Okay? So let's go ahead. Suppose S is a subset of SL and T is a single formula. Say that T is a logical consequence of S if there is if whenever a valuation V satisfies S, then V of T is true. Okay, maybe I should go back a bit to this previous one. Yeah, whenever we say that S is satisfiable, yeah, so this particular valuation, here we write V of S is true. What is the meaning of V of capital S being true? That V of small s is true for all S. Or I forgot to mention this. V models capital S. Yeah, read V models capital S, or V is a model of capital S. So this is called a double turnstile symbol. Okay, let me write this thing for you. So this is a double turnstile. So this double turnstile is actually a semantic notion. Why semantic? Because we are talking about valuations. Valuations have to do with truth and false. And truth and false are human constructs. Yeah, humans understand them. So therefore this is a syntactic turnstile. Double turnstile. The single turnstile, which we will see today itself, single turnstile is a syntactic construct. Okay? So that is more about formality. This is more about understanding. And completeness theorem will say that those two are equal. Okay? So, let us go over it again. So say that S is satisfiable if there is a valuation V such that V of capital S is true, which means V of little s is true for all s, small s in capital S. All the formulas in S are true. In other words, what do we write? That V models S. Okay? And now let us come to the next definition, and what it is saying, that whenever V is a model of capital S, then V is a model of small t. Yeah, let me write that. In other words, if V models S, then V models T for all valuations. I mean this whole thing for all valuations. V. Now look at what's happening here. I mean this is a consequence. Whenever we think about consequence, then it's always an if-then type of situation. If this happens, then that happens. So this is also a material implication. I mean conditional implication. If V models S, then V models T. So when is this a logical, recall what is the truth value of implication. What is the truth table of implication? When do you say that P implies Q is true? When P is false or Q is true, or in other words, whenever P is true, then Q is true. Right? We are doing the same thing here. For all valuations, whenever S is satisfied by V, then T is satisfied by V. Okay, so it is a logical consequence. So we are given a bunch of statements, and from those statements together we can conclude something. In simple terms, in Boolean algebra terms, what it is trying to say is also very simple. That this T, this little t, actually lies in the filter generated by capital S. That's all. Little t lies in the filter generated by the logical equivalence classes of capital S. Let us look at an example, then you will understand it more. Oh yeah, and what is the notation here? We write T is a logical consequence of S if T is a logical consequence of S. Well, it's not a tautology, okay? One is in symbols, another one is in words. So there are two different ways in which we can use the double turnstile symbol. What is the first way? Valuation on the left hand side and a bunch of statements on the right hand side. And here we are saying a bunch of statements but only one on the left hand side, but only one statement on the right hand side. Okay, so let us look at an example. Without that we cannot really proceed. So for example, if I am given P and Q, then from that I can conclude P. Yeah, this is a no-brainer. Yeah, if there is a valuation which makes P and Q both true, then the same valuation will make P true. Then if there is a valuation which makes P and Q both true, then it will make P disjunction Q true. If there is a valuation which makes P and Q true, then it will also make P conjunction Q true. Now here, let us look at these things in the Boolean algebra sense. What is happening? The filter generated by P and Q that contains P. The filter generated by P and Q, because it's an upward closed set, it contains P disjunction Q. And because the filter generated by P and Q is closed under finite meets, it contains P conjunction Q. Any doubts? I'm not going to draw pictures because it's a 4-atom 16-element Boolean algebra. It will take a lot of time. But you can draw them and you can realize logical consequence is nothing but that a particular element lies in the filter generated by the left hand side. And you already know what is the meaning of filter generated by a set. Yes, it is the smallest filter containing that. And how did we construct that? By first closing it under finite meets and then upper bounds. Okay, so give me one other example of logical consequence. How about this? P implies P is a logical consequence of nothing. Whenever a valuation makes left hand side true, where every valuation makes left hand side true, what is the left hand side? Empty. There is nothing. So every valuation makes left hand side true and every valuation makes right hand side true. So this is actually a remark. What should I write? So nothing implies T if and only if T is a correct. Okay, so I mean you can always use it with empty set. This double turnstile symbol you can use with empty set. On the left hand side, the right hand side must be non-empty. Okay. So do you understand this now? Now there is some philosophical talk here that if I have some information and then I get some more information, then whatever I could conclude from the original information, that should still remain valid. In real life, this doesn't happen. We simply get confused. If I strongly believe that two of my friends are truth tellers, one person tells me P, another person tells me negation P, then I simply get confused. Whereas in this kind of logic, this is a very fundamental and classical but basic logic, which is a very crude approximation of human understanding. So if we get two contradictory pieces of information, then actually what can we conclude from that? If I have written P and negation P here, then what can I conclude from that? Everything, right? So basically, even if I get some extra information, then I'm not going to decrease my set of consequences. I will in fact add more things as I go along. And that the simple concept is that the filter generated by S and filter generated by S prime, which is superset, if S prime is a superset of S, then the filter generated by S is a subset of filter generated by S prime. So I am going to write down two different things. First one, another remark. So this is, let's say, remark 1 and remark 2. If S is contradictory and T is anything, then I can conclude anything from a contradiction. Okay, let us look at this statement again. Let me go back to the definition of contradictory. What is the meaning of contradictory? That for every valuation, there is a formula which is not true. So basically, capital S cannot be true for any valuation. There does not exist a valuation V such that V of capital S is true. So therefore, now come here. If S is contradictory, then the left hand side can never be true. So left hand side is always false. And in our definition of truth of implication, if the if part is false, then the implication is true. So no matter what I put on the right hand side, it is always true. Are you getting that? And the reason being simply that if S is contradictory, then it generates the whole Boolean algebra as a filter. Right? So any T is an upper bound of 0 and 0 belongs to the filter. So therefore, because of being upward close set, upset, we get that T lies in that filter. So contradiction implies anything. So basically, a liar can say anything. Right? You cannot really believe. Yeah, the right hand side is anything. Any nonsense can be derived from a contradictory bunch of statements. Okay, now the next part that I was talking about is called monotonicity. monotonicity of the turnstile operator or the logical consequence operator if S is a subset of S prime and they are both sets of propositional formulas and T is any statement, then if T is a logical consequence of S, then T is also a logical consequence of S prime. So monotonicity, we have heard this term before, right? What is a monotone map? Order preserving. Now which order are we talking about here? We are talking about the inclusion order, this one. S is a subset of S prime. So S can increase, but still the logical consequences, the original logical consequences are preserved. That is monotonic logic. So there are many logics which are non-monotonic. Yeah? Other logics, I mean human reasoning doesn't work in a monotonic fashion. Human reasoning works in a non-monotonic fashion in general. As I mentioned earlier, if two people tell me contradictory information, I fail to form an opinion about that topic. So whatever I already believe to be true, I won't be able to believe in the same things. But because this is mathematics, yeah, it's a very crude approximation of human understanding, this is a monotonic logic. Any questions? Okay. So, you are supposed to prove monotonicity in the tutorial. I have already given this problem. Once we know something is a logical consequence, actually we have a very good test for logical consequence. So let us write that. So I am just going to write it as a proposition. Okay, so the proposition says this. Suppose S is a subset of SL and P is an element of SL. Then T is a logical consequence of S if and only if S union negation T is very good contradictory. So T is a logical consequence. T follows from S. So obviously if I put capital S and negation T together, then I am bound to get a contradiction. Okay, so let us try to prove this. Okay, so what is our proof? Suppose S is a logical consequence, T is a logical consequence of S. What does that mean? S union T is satisfiable. Does it mean that? No. See, S itself need not be satisfiable. S itself could be contradictory. So if we start with this assumption, then S itself could be contradictory or S is satisfiable, and then there is a valuation which makes capital S and T both true simultaneously. So are you seeing the proof here? If S is contradictory, then S union negation T is already contradictory, because the contradictory sets are closed under supersets. Or else, if S is satisfiable, then there is some valuation V which makes S and T sat true. So that particular valuation will not satisfy that. But in logic, generally we do not write proofs using this way. We will use contrapositive over here. So how to write that? So suppose S doesn't logically imply T. Suppose T is not a logical consequence of S. Then what will happen? Then there is a valuation. There is a valuation V such that what happens? V of capital S is true and V of small t is false. Very good. Then from here, what can I conclude? So for this valuation V, V of capital S is true and V of negation T is also true, i.e. V of S union negation T is, so therefore what can you say about S union negation T? It is satisfiable. So not satisfiable means contradictory. Very simple to understand. So we assumed that S logically implies T doesn't happen, and we concluded that S union negation T is not contradictory. Please understand that not contradictory means satisfiable, not tautologous. And not satisfiable means contradictory. Tautologous was anyway too good to be true. Tautologous means it is a bunch of tautologies. We don't want to talk about it. This is very rare to happen, being tautologous. Okay, so this is one part. And another part would be, we will again prove using contrapositive. We are not trying to prove anything using contradiction, only contrapositive. So suppose, which side was this? I mean, if I want to write the implication side, which one did we prove right now? Right. So this was this implication, and now we are going to prove this implication. So suppose S union negation T is not contradictory. What does that mean?
Satisfiable.
Is satisfiable. Okay, then what will happen? What is the meaning of satisfiability? Then there is a valuation V such that V of S union negation T is true. Therefore, V of S is true and and V of negation T is true. Therefore, V of S is true and V of T is false, and therefore S is not logically implying T. Well, actually, it was just the if and only if for this. Yeah? But hopefully you understand what we did. Any problems here? Okay, so at this point, perhaps it is appropriate to describe what is a theory. So in mathematics, have you come across some names which are called theories?
Cauchy theory.
Huh?
Cauchy theory.
What is meaning of Cauchy theory? I have never heard of that.
Complex analysis, like our self introduced like that, like theorem.
Cauchy theory.
Theorem like it is said like.
Okay, I don't know that it's called Cauchy theory, but any other names? Group theory, yes. Group theory or ring theory, number theory, field theory, linear algebra is also a theory. Category theory, okay. And I mean analysis, etc. are also theories. Have you heard of theories in physics? Field theory, also in physics. Then string theory, yes. Then in chemistry, have you heard of any theories? Arrhenius theory of acids and bases, yes. So there are so many theories around in each subject. So what is the meaning of theory? Somebody theorizes something, somebody tries to understand some real life phenomenon in case of physics and chemistry or biology, and then they try to experimentally show that their axioms are true. But it often is the case in case of physics and chemistry theory, like scientific theories, that one theory is not good enough. Yeah? After some point, somebody comes up with some examples for which this theory doesn't explain anything. It doesn't fit. So therefore, you have to update your theory. You have to go somewhere else, like somewhere deeper, and then come up with a new theory. Then again, until someday somebody disproves it, it remains valid. And that's how scientific theories develop. In case of mathematics, it's much simpler. Yeah? Mathematics says that it should just be a bunch of statements put together which are simultaneously true somewhere. So basically, a theory is nothing but a satisfiable set of formulas. It's a very simple definition. So whenever we are writing T is a logical consequence of S, if S happens to be satisfiable, then S is a theory and T is a theorem of that theory. So everything is if then. So mathematical theory is simple to understand. So let us write down the definition. Given a propositional language L, S subset of SL is a theory if S is satisfiable. we don't want to be contradictory. Yeah, that's the only minimum requirement for it to be a theory. And if S is a theory and T belongs to SL satisfies that T is a logical consequence of S, then we say that T is a theorem of theory S. So without you knowing, we have been talking about theorems and theories in this lecture. So mathematical theory never tries to impose anything on the real world. It just says, if this, then that. That is the difference between scientific and mathematical theories. Any questions? Okay. So let me check if something else is remaining from this part. All right. There are a couple of statements which I can write down. Yeah, I mean you will easily see them to be true, and you will prove them in tutorial, but I should mention them in lectures anyway. So suppose S is a subset of SL, T, T prime, U are particular L formulas. Then first thing, if U is a logical consequence of S, T and T prime together. Sorry, I shouldn't even say if. I should just say this, if and only if U is a logical consequence of S and T conjunction T prime. I mean, see, in practice, even though this S appears here, that S is irrelevant. Yeah, what we are really saying, like even if S is empty, if U follows from T and T prime, then U follows from T conjunction T prime. So, yeah, nothing much is happening here. Second thing, now this particular statement gives you a connection between logical consequence being an implication and the implication itself. So if U follows from S and T, I mean that happens if and only if T implies U follows from U, S. So you can see that T just changed sides. So basically, if S is empty, then what is happening? U follows from T if and only if T implies U is a tautology. So this logical implication is also less equal sign in the Boolean algebra. Especially when you are just comparing two formulas. Okay? Now, if you have understood this, then let me set some background for the syntactic version of the turnstile operator. So right now, if I say that T is a theorem of a theory S, or in general I just say T is a logical consequence of capital S, what does that really mean? It says that whenever left hand side is true, then the right hand side is true. So everything depends on truth. But now my question is, can we remove dependency on truth altogether? We don't have any true or false. We don't have any human understanding involved. We would like to teach this to a machine. When does T follow from capital S? Well, if I am given P and I am given Q, then I can conclude P. Is there any logic involved in that? Not really. Yeah, I mean, I am concluding P from P and Q. Even if I am given P conjunction Q and I am concluding P from that, there is still no logic involved in that. So, if I can develop a set of rules or a bunch of statements which are true, which I teach to a computer, then perhaps I can develop a, I shouldn't say theory, but this is a meta level thing. If I develop a theory to mimic human understanding, and that is entirely formal. Like if this happens, then that happens. So for example, modus ponens, if I somehow have concluded P implies Q and I have concluded P, then I can conclude Q. Now there is no logic involved. I mean, of course there is human understanding involved, but I can formalize this rule. Whenever a computer says P implies Q and P, okay, conclude Q. So I can abstract out some ideas and write them in the form of rules. Well, these rules are termed as calculus. Calculus is just a bunch of rules. Yeah, this is not your usual analysis calculus, but this is a proof calculus. We are going to teach a machine how to write proofs, how to write formal proofs, and this is called a deductive calculus. So, what does a deductive calculus consist of? It consists of some axioms and it consists of rules of inference. So, axioms in this case are just going to refer to something very simple. They will be tautologies. Does anybody have any objection about using tautologies as axioms? And then we will use rules of inference. And then we will formally define what is a proof. So right now we know when T is a logical consequence of capital S. In the next lecture we are going to see when T is a deductive consequence of capital S. And whenever we do that, I mean, it's our choice right now. Yeah, at meta level we are working, we are declaring that a bunch of statements are axioms and a bunch of things are rules. Then the first thing we should ask when we do that, are these bunch of statements true? I mean, the axiom should be true. So we are going to choose them as tautologies. And whether the rule of inference is also valid. Right? So rule of inference being valid has to do with this implication, if this then that. So modus ponens is obviously valid in our brain, because if P implies Q is true and if P is true, then Q is true. That's valid. So this is the so-called soundness theorem. Everything is sound. Sound doesn't mean my sound getting into your ears. Soundness means there is no problem with it. And conversely, which is going to be a major portion of our propositional logic syllabus, that whenever T is a logical consequence of S, then our deductive calculus is strong enough to provide a proof of T from capital S. Okay? If T is a logical consequence of S, then using our rules we can provide a finite length proof of T from capital S. That is Gödel's completeness theorem. Okay, so that's our next plan. We are going to follow Hilbert style calculus. There are different calculi for proof theory also. There is natural deduction, there is Hilbert style, but we'll follow Hilbert style because proving the completeness theorem is easier with Hilbert style calculus.